All right, so good morning everyone and welcome for this 10th lecture on artificial intelligence. So the topic of today will be a bit different than what we've been talking about before. So mainly the purpose of today's lecture is to show you how some of the tools we've been studying, like probabilistic models, but also neural networks, can be used to solve tasks that are maybe a bit more concrete than the kind of tasks we've been talking about so far. And so basically the question that we'll be interested in today is the one of trying to talk to some kind of artificial agent, and so that would be one task, but also to try to be sure that that machine would understand what we say in some way, right? So we'll consider three tasks: machine translation, so how to translate a piece of text from one language to one another. Then we'll consider the task of speech recognition, which is about how to translate a speech waveform into a piece of text. And then the final task will be the opposite, how to go from text to speech. So we'll frame these three problems as sequence-to-sequence mapping problems, meaning that we'll formulate our three problems as the problem of starting from some sequence, and this sequence can be either text or a waveform, so text like the one you see here in English, or waveform which would correspond to speech. And then what we want to do is to find some function or to define some probability distribution which would map this input sequence into either another output sequence or to a probability distribution over sequences. And so for example, in the case of machine translation, we would want to map sequences from one languages, so sentences, for example, written in English, to sentences written in French. For speech, well, we would like to map a sequence of sound, basically a waveform like this, into now a sequence of characters or words in some language, and supposedly in the same language as the speech. So for example, to form an English sentence. And then the third problem, text-to-speech synthesis, will be the one of doing the opposite. So we'll start with an input sequence, which is, for example, written in English, and then we'll try to synthesize or to produce another sequence, an output sequence, but now which will be a waveform like this. And so we see that the tools we've been studying so far, the probabilistic framework we've been using a lot, can also be used to solve these kind of problems. And so that's one way, and that's the most traditional way, I would say, to use to solve this task. But we also see that nowadays most of these tasks are solved in using neural networks, and we'll see also briefly how you can use neural network to solve these three tasks. All right, so we'll start with the first one, the first problem, which is machine translation. So machine translation is the problem of automatic translation of text from one natural language, which I will call the source, to another language, which I will call the target. And of course, we want to produce this translation while preserving the meaning, the semantic of the source sentence, right? So for example, if you go on Google Translate, could type a sentence like this in English, which says, "Our intelligence is what makes us human, and AI is an extension of that quality." This is a quote from Yann Lequin. And what you would like to have as a system is a system that would translate automatically this piece of English text into, for example, a target language, let's say French, and so you would expect the translation, for example, to be notre intelligence est ce qui fait de nous un humain, et l'intelligence artificielle est un prolongement de cette qualité. And so that's basically what we want to achieve. So this system, Google Translate, is itself based on some of the things we'll see today. It's mainly based on neural networks, but a few years ago it was rather based on the first approaches that we'll cover. And so my first question, so given what we have, what you know so far, how would you engineer yourself a machine translation system? And so if you have some ideas, please just dump them into the chat. But what would be the first approach that you would use to produce a system that would manage to translate sentences from one language to one another? Don't think too far. Any solution is good. I just want to have your opinion. So to have an algorithm based on existing text, yes. Words to word, obviously. Yeah. So a very straightforward and the most direct approach is indeed the one of creating a dictionary. This is one of the solutions in the chat, in which you would basically exhaustively have a list of mappings from words to words, or maybe from phrases to phrases, right? And then you'd use this dictionary to for the translation, where you try to match each one of the words or each one of the phrases in the source sentence into the target sentence, right? So you would say, for example, that our is mapped to notre in French, and so you would just replace our with notre, intelligence with intelligence, is with a, and so on and so on. If you do that, it may not lead to a perfect, it will not, definitely not lead to a perfect translation. We'll more or less understand maybe what you mean, but you'll be far from a good translation. And one of the main issue actually with this kind of system would be that we may not have a one-to-one mapping between languages. So we may have languages in which a single and same word has different translations. So for example, if you look at the word top in English, it may have different meanings, right? But we would still use the word top in English, while for example the counterpart in I think it's Japanese would correspond to distinct words in this target language. So the issue would be if you see the word top in English and then try to produce a Japanese translation, which one of these translations should you pick? Because now you don't have a one-to-one mapping, you have a in this case 1-to-9 mapping. And so it becomes a bit more complicated. And of course, then that means you would have to reason about what's the context around this word, around top. And from this context, then you will be able to infer which is the translation that you should pick, right? But to do that properly, you already understand that you need to do something which is much smarter than just doing one-to-one mapping and looking up your words in the dictionary and then replacing that word with the associated translations. More fundamentally, I would say that any translation system, machine translation system, should also in some way be able to understand I would call what I would call the physics of the world, as well as languages. And so, for example, if you And this is an example that I tried again a few days ago, so this is still an issue even for today's system. So for example, you type this sentence in English: the soccer ball hit the window, it broke into 1,000 pieces, right? That's a simple English sentence. And then if you try to translate this sentence into French, then what you obtain as a translation in today's Google Translate system is: le ballon de football a frappé la fenêtre, il s'est brisé en 1000 morceaux. And of course, here you already, I mean, for us it's obvious. There is an obvious mistake, which is the one that it, the word it from English, has been wrongly translated to il in French. But actually, to be able to understand that it should be translated to elle in French, we have to understand exactly what's the meaning of these sentences. And of course, only the window can break into 1,000 pieces. And so when you translate it into French, it should refer to that window. But to be able to do that, you need really to be able to understand what these sentences are about, right? And so this is what I'm saying. In order to make proper translations, you need to understand the physics in addition to language, right? And this is still an issue with today's system. Regardless of how they are implemented, they are still failing on these kind of problems. Of course, they've now reached good performance, but when it comes really to make produce translations in which you may have this kind of ambiguities, then it's still quite complicated to solve properly. All right, so before we go and dive into some of the approaches, let's just me say a few words about the history of machine translation. I think it's quite interesting because machine translation is actually the first, I would say, non-numeral compute task that was ever considered. So it's one of these first tasks that we ask computer to solve, which were not about simply solving some calculus problem, right? And so this is a problem which is not new. I mean, the first attempt date back to the 40s, end of the 40s. And since then, of course, we had much improvement, but it took some time. And so for 20 years, so from the late 40s to the mid 60s, there was a first, I would say, a first attempt at trying to solve this task with computers, but at that time, none of the programs, none of these attempts really managed to reach satisfactory performance. And so there was a famous report which basically said that machine translation is bad and the current system, at least at that time, will never reach, don't have a good enough performance, and we really need breakthrough to make a leap and to really make progress on this task. And so we had to wait until the 90s and early 2000s to really have a switch in the way we would solve these problems. And really the breakthrough was to view the problem as a statistical inference problem, which then would enable to better solve this task. And this is the kind of first approach that we'll consider together, is how to frame this machine translation problem into a statistical inference problem. So a data-driven machine translation, very abstractly, and would start with a corpus of text. So for example, a corpus of sentences in the target language. So let's say now the target language is English. We would start with, let's say, for example, these 3 sentences in English. And also we would have pairs of sentences from the source and the target languages, right? And these pairs would be aligned, right? Meaning that we would know that this the elements of these pairs would correspond exactly to the same meaning. And so, for example, we could have pairs from Spanish to English, and we would have, for example, this pair where the input is in Spanish would be hasta pronto, and then the output would be see you soon in English. And then the goal would be then to take this data in some way in order to build a model for translation, a probabilistic model for translation, right? So we'd like to find a way to mix all this information in order then to be able to also translate sentences which would be novel, right? And this is really what made it difficult with the previous and the early systems, is that it was really difficult to generalize or to produce translations for sentences which were not part of the initial corpus, right? But this is precisely what we'll try to do because there is no way we'll be able to produce an exhaustive corpus of pairs of sentences from one language to one another. However, maybe what we can do is to maybe collect information clue from sentences which we decompose into smaller elements, into smaller units, and then to use these smaller units to then be able to translate new and novel sentences, right? And so, for example, this is what you see there. This would be a new sentence from Spanish. And you see that it's composed of words which is part of the original sentence aligned parallel corpus. So, for example, these three first words are the same, and then pronto is also part of the second pair. And so for us, it seems easy if you know that this is the translation of I will do it tomorrow, and this is the source for see you soon. Then by just reasoning for a bit, you can guess then the translation for this one would maybe be such that you just take the first part of this sentence in English and then you combine it with the last part pronto of this other sentence. And it is, when you combine these four words together, the proper translation should be I will do it soon, right? Which is I will do it, io lo haré, and then soon, which corresponds to pronto. Okay? And so this is the kind of things we would like to do automatically from a corpus of data which may not be exhaustive, right? So there are different ways to achieve that. But one thing that this translation system must do is to model the source and the target languages in some way, right? And mainly, the system will vary in the type of models they will use. And so there are different, of course, flavors, I would say, of machine translation system, but most of them are based on some knowledge representation, which is some intermediate representation, which is computed from the source sentence. And then so you go from the source sentence into this intermediate representation of the sentence. And then from this intermediate representation of the sentence, then you translate, you decode this representation into the target language. Of course, you may have different levels of representation of these sentences, right? And this is what we'll just see in the next slide. So what you could have is that, okay, you would start from sentences in English. And so this triangle, this diagram is called the Vauquois triangle. It's just a diagram of the choices that you may have for a machine translation system when it comes to deciding on this intermediate representation that you would use in order to produce the translation. So you could go from the lexical representation, like the original representation of the sentence, and then parse the sentence into maybe its syntax, in which you've identified the subject, the fact that John is a noun phrase, that loves is a verb, and that Mary is a noun. You could also, and then from this representation, maybe you could then produce the corresponding, let's say, French syntactic representation of that same sentence. and then from this syntactic representation, decode it back into the lexical representation in a proper French sentence, right? So you could do it this way by going through the syntactic representation, but you could also maybe go a bit further and use a semantic representation from specific to the source and then to the target languages, in which you would have a concept like loves between two persons, John and Mary, right? And in French, that would correspond to the concept of M between these two guys, Jean and Marie. Or you could also have a unified representation, knowledge representation of that sentence, which now would no longer be tied to a language, but would be global to all of them. And so you could also try to map your sentence into this semantic representation, this global semantic representation, and then try to decode this representation back to the French sentence, right? And so this is this first bullet in this list. So some systems analyze the source language text all the way into an interlingual knowledge representation and then generate sentences in the target language from that representation. And then you may have other systems that are based on a transfer model, and they will keep basically a database of translation rules, and then whenever the rules matches, they translate directly, right? And so what will happen then, which is somehow similar to this dictionary-based approach, would be that, or it's also a bit similar to our reflex agent in some way. You would have some rules that are defined at any of these levels, and that could be used then to produce the corresponding representation on the same level, right? So you could have a transfer model, either that would go directly from the lexical representation in English into the French lexical representation here. And so this is what is represented by this dashed arrow would be a model, a transfer model operating at this level. But you could have transfer models also at the syntactic or the semantic levels, right? And you would have, of course, other set of rules, but you could. It's quite obvious that you could define also this kind of rules to go from English syntax into French syntax. Right? So, but still, this would still be close to this dictionary approach, even with these refinements, and would still have the same issues. So instead, we can frame the problem as a statistical inference problem. So this is what we'll do. So to translate an English sentence E into a French sentence F, so E for English and F for French, what we'll do, or what we'll try to find, is the sequence or the sentence F star for which the conditional probability is maximum. The conditional probability of that sentence F condition on our input sentence E is maximum, right? The issue is, of course, how do we define this conditional probability between sentences? And then, even if we have that, how do we find this maximum F sentence? And so this is where we'll make use of our data, right? So we'll basically define P of F given E, which we'll call a language model, and we'll learn it from a bilingual corpus. So from a corpus in which we have these mappings, these pairs of English, for example, and French sentences, right? And so what is important now is that we'll decompose the problem into simpler problems, and we'll split the English sentences to be translated into phrases, and then these phrases, then it's very likely that we would have seen them before. So maybe this is something I should say also, because this might be misleading. So In English, a sentence is translated as a phrase in French, but a phrase in English corresponds to locution in French. So phrase here refers to locution and not to sentence, right? So we'll basically start from English sentences, decompose them into smaller units that we'll call phrases, and then we'll try to build our statistical model at this level of the representation. And then from this, we'll be able to recompose these phrases into sentences using also a statistical model, right? So what we'll do is that the corresponding French phrases will be reassembled to form a French sentence now that would make sense. Right. And so concretely, well, the recipe is quite simple. We'll start from an English sentence E, and then to find the corresponding translation F in French, we'll proceed into 3 steps. So we'll split the sentence into phrases. So we'll split E into smaller units, phrases that, let's say, for example, E1, E2 to EN. And then for each phrase, EI, we'll choose a corresponding French phrase FI, right? And to do that, we'll base our choice on the phrasal probability, which we'll have to learn or to define or to estimate in some way, between the phrase FI and the phrase EI, right? So we'll use the notation PFI given EI to denote this phrasal probability, which basically should just interpret it as the probability that FI, the phrase FI, is indeed a translation of the phrase EI. You can already see that this is where we'll be able to solve this ambiguity problem. The fact that a same word may have different translations would just be handled directly by the fact that, for example, so if EI is the word top, then we'll have a probability distribution defined, for example, over, of course, all the vocabulary of let's say, the Japanese dictionary, but we'll put density, we'll put probability only on the words that could be reasonable translations, and so that means we could put that probability on not only one but on several different words. Right. Then we'll also define, because a sentence is composed of phrases, but from one language to one another, the ordering of these phrases may change. So we'll need to define what is the permutation that should apply to obtain a good translation. And so to do that, we introduce a new variable di, which will correspond to the number of words that some phrase fi has moved with respect to fi minus 1, right? And so this variable then will be able to use it then to know when basically to know where we should put the phrases that we've translated to reconstruct, to reassemble the full sentence. Right? So as an example, let's consider this input English sentence. There is a smelly wumpus sleeping in cell 22, and which would like to translate into French. And so in French, a good translation would be il y a un wumpus. So the wumpus is a monster that this year we have not seen, but which was part of this lecture 2B, the optional lecture about constraint satisfaction problem. But so it's just some kind of monster, whatever. Il y a un wumpus malodorant qui dort dans la cellule 2. Right. So what you see is that we've split the English sentence into phrases. So we have a first phrase which is there is a, then a second which is smelly, a third which is wumpus, a fourth which is sleeping, and then a last which is in 2. And then for each of them, we'll compute, for example, will associate a corresponding French translation. There could be several of them, but let's say the ones that we pick is il y a un for there is a, then malodorant for smelly, wumpus for wumpus, qui dort for sleeping, and then a de deux for into two. Right? And then, of course, in French, the ordering of the words would be slightly different. In particular, we would put the adjective malodorant after the wumpus. And so this is where you see that there would be some kind of distortion between those two sentences. Right? From the English to the French, we would have to distort basically the positions of the phrases in order to construct a proper French translation. All right, so we're actually almost there. So now we'll have to define the probability, the conditional probability P, F, and D. So the probability of some French sentence with a vector of values for the distortions given some input English sentence, right? So we'll define that probability that the sequence of phrases F with distortions D is a translation of the sequence of phrases E, right? So remember that we'll just consider that a sentence is nothing else than a sequence of phrases of these smaller units. So if we assume that each phrase translation and each distortion is independent of the others, then we could define, but this is a choice and we could do things differently, but we could define this probability, this conditional probability distribution as some product over the individual phrases that compose the sentences, right? And in which we define each factor of this distribution as the conditional probability of course, the corresponding output phrase Fi given the associated input phrase Ei, and the distortion that we should apply to this output phrase. And now the best, so the issue now, so this is something we could define, and then we could just maybe try to solve for F and D. So we could try to maximize this probability, this conditional probability for F and D given E. The issue is that we are dealing with objects that are discrete, they represent world, right? So that means there is not really a much better algorithm than just brute forcing the solution. So that meaning to just enumerate all of them and then to compute to return the one for which the probability is the highest, right? And so this is, so if we were to do that, that would work, but it would not be practical, and it could not, you wouldn't be able to translate anything which is longer than a few words because there is a combinatorial explosion. So, for example, if you have a corpus in French with only 100 phrases, and this is quite small actually, for each English phrase in the corpus, then that would mean there would be 100 to the power of 5 different 5 phrases translations for that input sentence in English. And then for each of them, there would be the factorial of 5 different orderings. So the number of combinations would just grow too quickly for this to be effective. So instead, so again, that means we'll have to resort to approximations to find a solution. And so one of them is to use search algorithm like local beam search with a good heuristic that then would estimate the probability, Yeah, so you should use beam search, local beam search with a good heuristic, and that would work quite well. And indeed, this is what has proven to be effective in most of these translation systems, or at least the ones that are based on this formulation of the problem. All right, so now we have basically a language model, right? So we've defined this. The issue is, how do we build it in the first place, right? And so to do that, what we would need to do is to find parallel text. So to find text that are exact translations of one another. So for example, English sentences with their corresponding French sentences. We would have then to segment this text into sentences, to align the sentences, and then to split the sentences again into phrases, to align the phrases from one language to another. From these alignments of phrases, we could extract the distortion factors, so these D values here. So that means now by just looking at this data and then just estimating empirically from this value the distortions, we could build a model for PD, right? And also from the alignment of the phrases, we would also be able to estimate or to build an approximation for PFI given EI, right? Because for each pair that we have aligned from our data set, that means we would have an example of EI and FI, right? And so just by going over the data, we would have several of them, and maybe for a same EI, then we would find different FI values, right? But that's fine. At the end, we just build them into this conditional probability distribution. Right? And so if you were to do that, then you would obtain a system that would work more or less well. Not state of the art, not at all, but would produce reasonable translations, right? Even if they wouldn't understand anything about what is going on in the sentences, the translation would be reasonable. So this kind of formulation, statistical machine translation, is basically what was really the main design, I would say, of machine translation systems from the 90s up until, I would say, 2010. But nowadays, this formulation is quite obsolete, and none of the state-of-the-art systems are actually based on that. They are all based on neural networks of various different kinds, again, but most of the translation system, if not all, are based on neural networks. And so these neural networks are variants or improvements to the kind of neural networks we've seen briefly in lecture 7. But for example, one of them was these recurrent neural networks. You can actually use this same kind of networks to build translation system because you can understand what you need is just to be able to get as input a sequence, which is something you can do quite naturally with a recurrent neural network, and then to produce as output another sequence, which is also something which is quite straightforward with a recurrent neural network. But it is not the only one, not the only architecture when it comes to neural networks. You can also make use of convolutional neural networks if you need, for example, to model spatial dependencies. So adding convolutions to recurrent neural network is something which is usually helpful when it comes to dealing with text and machine translation. And then the final kind of architecture, which is more recent, is the transformer architecture. And so this is a quote, for example, from Google's regarding their neural machine translation system. It's from a few years ago, but one thing they said is that when they switched to a neural network-based machine translation system, while before they were using this kind of statistical driven approach, they reduce translation errors by an average of 60% when compared to this previous technology. And so one example, but we won't go into too much details here today, is, for example, a recurrent neural network that would be based on attention mechanism. And I like this one because this is something which is quite intuitive and which resembles the kind of things you would do when yourself you translate a sentence. And so the way it would work is that you would start with some English sentence. So for example, a long time ago in a galaxy far, far away, this is the English sentence you would like to translate, and you would like to translate that, let's say, into French. If you were to do that, the first thing you would do as a translator would be to read the sentence before trying to make any attempt at translating it. You would read it, right? And this is exactly what you would do also with this neural network architecture. You just process this sentence with a recurrent neural network. So that the recurrent neural network would just read the sentence. It would read it forward, so from left to right, but also, because why not, from right to left. And from these two readings, it would build then an internal representation of the sentence, right? And from this internal representation, then would produce the output sentence. So when you make this reading, basically the neural network is basically mapping the original sentence into some intermediate representation, except that now, which is quite different from this older system, this intermediate representation is learned, it's not hard-coded in the program, right? It's just something which is learned by the neural network, and the neural network will basically discover what is a convenient and efficient intermediate representation in order to produce good translations, right? But on principles, it's the same kind of idea. You read the sentence to map it into some intermediate representation, and then from it onward, you will decode it into the target language. And then what is nice with this architecture is how then the tokens, the output phrases, are produced. And so the way the way you would usually do it would be to start wondering what is the first word I should produce given this sentence. And so you would basically read maybe the sentence again, and then you would focus your attention on maybe a few words. And your attention would be certainly for this phrase at the near the beginning of the English sentence. So a long time ago would be translated into il y a bien longtemps. And when you produce this translation, you don't really care about what will happen before, right? Because you know quite well this is not important for the translation of the first word in the output sentence. But then as you would move on and then produce the next words for the translation, you know that now that you have translated this first part, they are not so important anymore. And for example, if you translate in, you know that, okay, you should really focus your attention on it and maybe the words around, but maybe not the words that are too far away from this word, right? And so you would produce dans, and then in a galaxy far away, so galaxy far away, you would translate it into dans une galaxie lointaine, and then far away. And then when you translate the end, also now you put all your capacity, your translation muscles, I would say, on the last word, because you know quite well the first word in the sentence are no longer that important. They are no longer really needed to produce the remaining part of the sentence, right? And this is exactly what this neural network architecture is trying to reproduce. So there is some kind of something which is called an attention mechanisms, which will basically reweight part of the intermediate representation depending on what you have already translated and what is the current word that you translate, right? And then you will proceed like this until you arrive to the end of the sentence. Right. So now let's move on to our second task, which is the one of speech recognition. Right? So in speech recognition, what we'd like to do, for example, would be able to talk to a machine by really talking to it, and then we would like it to understand what we are saying. Right? So that means we'd like to go from speech, spoken English or spoken French, into a piece of text. Right? And so this is something which is used, for example, in any of these connected devices, like Google Assistant, Siri, Alexa, and all these things. You can talk to them, and then you expect them to understand what you are saying. Again, we can frame this problem as an inference problem. And so we can frame recognition as inference. And more specifically, we can view the problem of speech recognition as an instance of the problem of finding the most likely sequence of state variables wi, which is our output sequence, given a sequence of observation y, which is the waveform that we produce. So you can view this problem basically as some kind of Markov process, right? In which you would have hidden variables or states, the x variables that we are considering when we talked about that in lecture 6, and this would correspond to words. But the issue is that we don't directly observe these words. The only thing that you observed are utterances of these words, right? So like a spoken version, a speech version of these words, and so this is this input sent in this input sequence, this waveform. And what we would like to do is to, given these observations, to determine what is the sequence, what is the most likely sequence of our state variables of, so concretely of these words, right? So hidden state variables would be the words, and then the observations would be the sounds associated to these words. The input audio waveform from a microphone would be also converted maybe into a sequence of fixed size acoustic vectors, yes, in a process that we would call feature extraction, yes. So of course we would not maybe work directly with the waveform itself. We would have maybe to process it, so to apply some preprocessing procedure to convert that into a format which is maybe more manageable to define our mapping between y and w, right? And so this process, we'll call that feature extraction. And then finally, we'll have a decoder which will attempt to find a sequence of words, so the sequence of states, w from 1 to l, which is the most likely given that observation sequence y from 1 to t, right? And so we'll frame our problem as the one of finding the words, the input, the sequence of words, which is the most likely given our sequence of acoustic vectors y. And so you should note that this vector, these sequences, will not have typically the same size, right? Because so for example, to represent this sentence, you just need 4 words, so we'd have a sequence of 4 elements. But to represent that same sentence as a speech sequence, then you would need a sequence which is much longer than 4, right? You would have sounds that are combined together to produce the corresponding speech, but you would need more than 4 sounds to do so, typically. All right. So again, since modeling directly the conditional probability of the words given the acoustic vectors y is difficult, what we can do is to work in the opposite way and then to invoke the base rule again to solve an equivalent problem, which would be the one of finding the words sequence from 1 to L, which is such that it maximizes the product of its prior probability under some language model times the likelihood of observing this sequence, some particular sequence of acoustic vectors, so y from 1 to t, given this word sequence. Right? And reframing the problem in this way makes things much easier because defining P of W is something which can be done. It just boils down to defining a probability distribution over sequences, which we can estimate simply by from data. And the second term, or the first factor, is what is known as the acoustic model, which is basically the relation between words or from words to acoustic vectors. And in this direction, it's usually easier to define. While if you were trying to go from acoustic vector to words, then that would be more complicated. All right, so let's see how we could define such acoustic model, right? To define this conditional probability of y given W. Well, basically, So before we do that, maybe I can explain this, which is basically the overall architecture of this system, which I've talked about, which is to go from speech to words again. And so we would have several steps. We would have this first step of feature extraction to go from speech to feature vectors. So these feature vectors would be these y acoustic vectors, right? And then we would have to define several pieces. We would have to define the acoustic model. Maybe we would need to do that pronunciation dictionary, which we'll see in the next few slides, and then the language model. And then we could recombine all these things together, for example, in this way, then to produce or to be able to decode the speech into a sentence made of words, right? So let's see, now we'll see how to implement each one of these steps. So we'll start with feature extraction, and then we'll talk about the acoustic model. All right, so feature extraction basically seeks to provide a compact representation y, a sequence of acoustic vectors of the originals of the original waveform. This acoustic vector should be designed such that it minimizes the loss of information that discriminates between words. Right? So typically we would need to be able to process this sequence of sounds into a way where maybe, for example, we would have removed noise or other part which is irrelevant, as long as we keep what is really necessary for us to distinguish the words that are spoken in this sequence. Right? And so there are several solutions here, but one of the most widely used encoding scheme or feature extraction preprocessing algorithm is called male frequency subtract coefficients, or MFCCs for short. So we'll not go into the details. Maybe I suppose you will see that if you follow, for example, classes in signal processing, but it involves taking basically the original waveform as input, then doing various transformations like windowing, taking the FFT, then some modulus of that, filtering this again, taking the log, transforming, and then at the end, basically what would happen is that you would have transformed this long sequence into a typically short array of just a few values. A vector, for example, in this case of 4 coefficients. right? And this is something you would do, for example, on small segment of the waveform, and then that you would apply repeatedly, then to produce the sequence of acoustic vectors, right? So this, what you see here would be one of these acoustic vectors, but then you would produce several of them by sliding basically the algorithm, this preprocessing procedure, over the whole input sequence. And if you do that, then you would arrive, for example, to this representation. So we would start from this waveform, right? And then we would transform it into MFCC coefficients, or rather a sequence of MFCC vectors, right? And so here what we would have is typically 13 MFCC coefficients, and we would compute that at some small interval. I don't know, maybe one every 10 milliseconds or something like this, right? And so we would have now this acoustic representation of that signal, and this is the representation that then we'll use to produce the translation, right? This is from this on this representation that we will try to, for example, estimate this conditional probability. So meaning we'll try to define a relation between words and their corresponding acoustic vector, or their corresponding MFCC vectors. All right, but to do that we need an acoustic model. So an acoustic model is something which defines basically how a spoken word W is decomposed into a sequence of basic sounds. And so a word would be split into k such sounds, and these I would say these units are called phones or base phones, and they would correspond, for example, to vowels or consonants that you would have in the word. And so, for example, one okay, so let's say these units, these phones, let's call them Q, right? So what we would have is that a word could be viewed itself as a sequence of these phones, right? And this sequence of phones, we'll call that the pronunciation of a word. And so we would have that a word now is associated to a pronunciation made of k different phones, right? And of course, what could happen is that a same word may have different pronunciations. For example, if we are dealing with accents, we could have the same word pronunciated in different ways. So that means for same W, we could have maybe distinct pronunciation sequences like this, right? But so, for example, as an example, if you take the phrase artificial intelligence, then some corresponding pronunciation could be this one, which is written in this language, which is basically mapping these symbols into a phone, and these phones basically are saying how you should pronounce this word. So depending on the language, you may have different, several of these phonetic alphabet or phonetic dictionary. So you have languages in which you have some phones, but in other languages you don't. That really depends on the language. But so, for example, this is the case of English or American English, in which you have basically all the base phones that may appear in English, how they are written in this kind of notations, and how you should pronounce them in terms of, for example, or rather examples of words which have this pronunciation, right, which include this phone. All right. So what we've done so far is that we've taken words, we've split these words into base phones, into basic sounds, right? And together, these basic sounds, or this sequence of basic sounds, are called pronunciations, right? As I said already, a same word may have different pronunciations, depending on the accents or the dialect that you consider for the language. But of course, if you want to build a robust translation system or a speech to text system, then you want to be robust to the different ways a word could be pronunciated. And so that means you would have to not only enumerate what is the pronunciation of each word, but what are the possible pronunciations of a same word, right? And so this is what you can do with these so-called pronunciation models, in which, for example, you see that for the word tomato, if you consider dialect variations, then there would be two ways to pronunciate the word tomato, in this way or in this way. To be honest, I cannot tell you how you should pronounce this one or this one. I don't speak phones, but if you manage, I would be happy to know about that. And also, you could include more variations in the language. So one of them is called co-articulation, in which, so that would basically extend the different pronunciations of the word tomato from 2 to 4, right? And you see that you could obtain each one of these 4 pronunciations by just following the arrows from the start to the end. And the numbers that you see on each arrow correspond to basically the preferred translation, or to the let me see, yeah, or rather to the probability of seeing or encountering this or that pronunciation in practice. Again, these numbers are something that you should collect from data and you should estimate from data. Right, so now we can represent words as sequence of phones, of different sequences of cones through this pronunciation model, but we have not yet associated these base phones, these individual sounds, into our observations, which are these MFCC coefficients, for example. So this is the last piece that we need to define. And so what we'll do is that we'll say that each base phone Q is represented itself by a phone model defined as a 3-state continuous density hidden Markov model, where, so in this way, so this would be a phone model for one of these particular sounds, right? And so what you see is that it would start from some initial state, hidden, and then it would transition from this state to, for example, the second state 2. And when it is in state 2, what would happen is that there would be a conditional probabilistic mapping between this state and some acoustic vectors, right? So finally, we would define how these y vectors are related to our words, right? Except that we would associate them at the level of states of our phone models, right? So at the beginning, the very first part, let's say, of the word could emit, for example, W1 or W2 vectors. And then, since we would model that as a hidden Markov model, either at the next step, we would either remain in the current state, or rather the next state would have the same value, or we would transition to a new value, right? For example, to the value 3. And associated to this value tree, then we would emit other observations, other acoustic vector y's. And then again, in this state, we could either remain with this value, and in that case, we would emit again this kind of W3 vector, Y3 vectors, or we would transition to state 4, which would be associated to other acoustic vectors, and finally, either we would not produce any acoustic vectors anymore because we would have pronunciated the entire phone, or we would keep being in this state and produce a bit more of these acoustic vectors. Right, so in this diagram, what you see is that this parameter, for example, A22, A33, so the parameters A, I, J, they basically correspond to the probability of making some particular transition from state Si to state Sj, right? And so this is how basically the Markov process would basically evolve through time. And then we would need to define how the observations are tied to these states, right? And this is what you do with these arrows. And in the case of, for example, this phone model represented here, what we would have is that the output sensor model would simply be Gaussians. So this B would be Gaussians. So for example, we would have that Bj or B2 would be a normal distribution or Gaussian distribution of some mean, which would be associated and specific to J, and with some covariance matrix sigma J. And then from this normal distribution, then we would have a density for any acoustic vector Y, right? So this is how finally then we'd be able to relate the Y values that you observed to states in phones, and then that means since states in phones are related to phones, right? That means we relate acoustic vector to phones. Then these phones are part of this larger pronunciation model. So now we would associate the acoustic vector to the pronunciation. These pronunciations are themselves associated to words, right? And so we would then have, you see how some kind of hierarchical fashion would have associated these acoustic vectors from these elementary units up to words, which we need to produce the translation. And so if we do that formally, what we would have is that the full acoustic model, so our mapping or conditional probability of Y given W, can be defined as a composition of pronunciation models with individual phone models, right? And so basically we would say that the conditional probability of Y given W correspond to the marginal distribution in which we have marginalized out all valid pronunciations Q of that sequence W, right? So for example, if W is just tomato, that means, and if we use this pronunciation model, then we would have two pronunciations. So we would have two different values for this Q variable. So we take this summation over all valid pronunciation sequences for our input sequence W from 1 to L, where Q is some particular is a pronunciation. So that means it's just a particular sequence of phones, right? And these phones, Q is a sequence of pronunciations of the words, right? Because this is a sentence, so you would have that you would have it to enumerate and to recombine all pronunciations for all words, right? And so Q would be just a sequence over pronunciations of words, over words, right? So we would say that P of this first conditional P of Q given the value is just the product of the conditional probability of the individual pronunciation in that sequence given the associated word, right? And now that we have listed or that we've decomposed our model in terms of this conditional probability distribution of the pronunciation, some pronunciation of a word. So that means basically this Q here would be, for example, one of these paths through this pronunciation model. Right? It could be, for example, this one above, this one below, or maybe this one if you consider this more complicated model. But this particular pronunciation is itself made of phones, right? And which meaning these phones can be themselves expressed in terms of their associated phone models. And so when you combine all these things together, now we would have a sequence of phone models given for that particular pronunciation associated to this word, right? And so this is what we can then do with the phone models. So what we would basically do is that we build this composite hidden Markov model by just concatenating all the constituent pronunciations and their corresponding base phones. And if you do that, then the acoustic likelihood would be given by the different ways these acoustic vectors could have been generated given a particular pronunciation of the whole thing. And that means we would need basically to loop or to consider all possible states, hidden states in our Markov process, right? We would need to consider all possible states, and then for each of them, we could associate the corresponding probability of the acoustic model, right? And so S would then just denote a state sequence through the composite model. And so if we have this particular state sequence, now we can just evaluate the conditional probability of acoustic vectors given this particular state values, right? And this would be given by this. And here we are defining everything in terms of the joint between the state and the y, just to make things more convenient, because we would be then marginalizing out this state. And so this is why you see these a variables that appear, because they correspond to the probability of transitioning from state I to state j. Right? And so that's it, basically. With that, we have everything that we need to estimate this piece. So P of y given W. I'm not saying this is easy to compute, but we have a proper model which is motivated by domain knowledge, how we think sound is related to acoustic vectors is related to phones, and then phones to pronunciations, pronunciations to words, and then words to sequences or sentences. All right. The last piece that we need is to compute or to estimate the language model that we need when we rewrote the conditional or the posterior probability in terms of this product of likelihood and prior. And so the prior probability of a word sequence, W, made of L word, would be given as could be, for example, defined as, so this is a choice again that you would have to do, but you could say that the probability of seeing word L, right, depends on the n previous words in the sequence, right? And then you would model the probability of a word sequence as the product of this individual probability or of this conditional probability on the words that constitute this sentence W. And so why we would do that is because then we would this is something we could estimate from data, right? We could just go over our corpus of text and then look at the n previous words and then just estimate what is the probability of seeing the word WL given this previous sequence. Right? And so if n is kept small, this is something which is doable. All right. So we have we now have the criterion. We have defined it. We've defined the two factors, the likelihood and the prior. Now the only thing which is left is to actually maximize this product. And this is called decoding, so to go from speech to text. And to do decoding, we have already seen an algorithm when it comes to hidden Markov models, which is the Viterbi algorithm, right? And the Viterbi algorithm, if you remember, is this algorithm that you can use to retrieve the sequence of states which is the most likely given a sequence of observations, right? And so the answer, the value which is returned by the Viterbi algorithm would be the sequence of words that you would use as output. Again, so this is nice, and you see how many of the things we've seen in the previous lectures can be used to actually build such a system. Of course, it may look a bit complicated, but what is important is that every step is actually motivated by what we know from speech, natural languages, and other things like this. So they make sense. And when you proceed in this hierarchical way, it's not that complicated actually, right? But to be honest, this kind of system shows limitations, and so none of the state-of-the-art systems are actually used based on this kind of approach are used nowadays. Instead, again, now all speech to text systems are based on neural networks again. So this is not surprising. But what is maybe more surprising is that most of the system, right? They may just take the very raw sequence of sound as input, and then directly produce the correct output sequence of words, right? And everything in between, which was motivated by domain knowledge in some way, and smart engineering and signal processing, all of these things, most of them can be just thrown away and replaced by a single neural network, which is not small, which is complicated by itself, but which will just learn everything by itself from data, right? And again, again, this is a field of research, so I'm just showing you one possible way to do that. But this is a picture of the speech-to system, which is based on a recurrent neural network. In total with 35 million different parameters. And what is nice is that this same architecture can be used to actually translate or to recognize different languages into text without any change or almost any change to the architecture. While, for example, if you had to adapt this system that we've just seen, which is actually quite specific to English and American English, because it's based on these phones and the way we pronounce, then all these values that are tying acoustic vectors to states, they are also quite specific. So the parameters here that you have internally in these Gaussians, they are really tied to the language. So that means we would have to re-estimate all these things. Maybe we would have to do some other steps. To use the same system for another language. Let's say we want to apply that same system to Chinese. That would be quite complicated actually. However, with this neural network approach, basically you don't have to change anything except retraining the neural network on a Chinese corpus or a Chinese data. So I will show you this video where they quickly explain the system, the speech, and they walk you through how it works.
Hi, I'm Ryan Prenger.
I'm Tony Han.
And we're research scientists at Baidu. And in today's video, Tony and I are going to talk about how we got deep speech to work in Mandarin. We first started working on speech recognition in English in 2014. After we finished our first deep speech paper, we wanted to get the system working in Mandarin Chinese.
我是一名工程师。
Now, Mandarin is considered one of the hardest widely spoken languages for English speakers to learn because it's so different from English. So we weren't sure how much of our pipeline would have to change to get a decent result in Mandarin. It turned out the end-to-end deep learning approach made switching languages way easier than we thought it would be. Traditional speech recognition systems have a lot of different components that have been added over the years to improve performance. Like there's a feature extraction part, a lexicon of phonemes that has to be built, and an alignment of phonemes to timeframes that is usually bootstrapped through multiple models. All of these pieces were put in because with certain datasets they helped, but the complexity of the pipeline made it harder to adapt to a new language like Mandarin. You'd need different features, a word segmentation step, a new lexicon, and so on.
The end-to-end approach we used in deep speech allowed us to achieve state-of-the-art results quickly without having to tweak all these components. Deep speech doesn't use specialized features like MFCCs or a lexicon of phonemes. We train directly from the spectrogram of the input audio signal. The neural network does all the tweaking. In fact, the biggest change we had to make for our deep speech system to work in Mandarin was increasing the size of our output layer to accommodate all the Chinese characters we used, which was around 6,000 of the most common characters.
We also found that architecture and system improvements in Mandarin also help the English system and vice versa. Thanks to that generality and the end-to-end learning approach, in just a few months we produced a state-of-the-art Mandarin speech recognition system. In fact, it was so good that it beat native Mandarin speakers in accuracy on our test set. Here's an example utterance that most Mandarin speakers can't transcribe at first. However, once they've seen the transcription from deep speech, it's usually clear what the speaker is saying. For more details, read the blog post, and for way more details, see our Deep Speech 2 paper on arXiv.
All right, so now moving on to our last task for today. I will not do a coffee break today because there is only a few slides left, and so I think I will be done in 15 or 20 minutes. So text-to-speech synthesis. So this last task is about doing the opposite of the previous task. So to start from a piece of text and then to generate this acoustic vectors, for example, or to generate a waveform directly, right? Again, so you could do that with more traditional AI approaches based on Acoustic Model, motivated by domain knowledge. You would arrive somehow to something which almost works, but you would not be very satisfied. I think that now you understand that, okay, you could do it, but this kind of approaches would quickly show limitations. And again, and this is actually one of the take-home messages for today's lecture. Most of state-of-the-art systems are based on neural networks. And again, for this task, neural networks are the best architecture that we have, the best system that we have. And so, as just a quick example for this text-to-speech, I will just walk you through this Tacotron 2 architecture, which is again a system which is based on sequence-to-sequence neural network. And that architecture consists of two components. Basically, again, a recurrent sequence-to-sequence prediction network with attention mechanisms, as similar to what we have seen for text-to-text translation, except that this recurrent network will take as input our text And then we'll produce not text, but we'll produce a sequence of, in this case, male spectrograms. Like this kind of something which is similar to these MFCC vectors. And then from these spectrograms frames, the second component, which is the vocoder, we'll just take them as input, and then we'll produce as output the actual waveform that we can listen to, right? And so basically this vocoder will generate time domain waveform samples conditioned on this predicted by the, as produced by the recurrent neural network from the predicted spectrogram frames. So the architectures now can become quite involved, but don't worry too much. It's still a neural network which is handling everything for you, except that now it's getting bigger and bigger, but you would start with some input text, which is your sequence of words. And then there would be some kind of character embedding which would happen. And then this embedding, which basically would transform the words into vectors. Then these vectors would be fed to convolutional neural networks made of 3 layers. And then that would produce now some internal feature representation of this sequence of characters. They would be fed to what is known as a bidirectional LSTM, so it's a flavor of a recurrent neural network. And that would basically again produce this intermediate representation that you need then to produce a translation, except that now this translation would be some kind of spectrograms like this, right? And to do that, you would again have this attention mechanism in the middle, which would be connected to another recurrent neural network, and convolutional layers and so on. So we really don't need to go into too many details here. That's not the purpose. But again, these LSTMs or these recurrent neural networks in orange would then produce now a sequence of spectrograms. And so this would be each one of the columns, each one of the frames that you see in this image. So that whole thing here, except for the green box, would be this first component, this recurrent sequence feature prediction network. And then the second component is the vocoder, which is that component which goes from the spectrogram into time domain waveform samples, right? And to do that, the architecture which is used in Tacotron 2 is known as WaveNet. Again, we don't need to go into too many details, just remember that it's again a neural network. It's called specifically an autoregressive neural network, which will then produce these final output values. So I can show you, or you can listen rather, to some samples that are generated with this architecture, this WaveNet architecture. Let's go there. So what you will listen to is this vocoder architecture, which is taking as input the spectrograms and then producing as outputs these waveforms, and that's what you will be listening to.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
And so you see it's working very well. It would be difficult to say that this voice has been synthesized, meaning that it's not a real voice. I mean, if you work a lot in this domain, maybe you could you'd be able to detect small differences that do not make it maybe as human as you would want. But if you didn't know about that, it could be difficult to say that this is generated by a neural network, right? And if you're interested, there are more examples. Of course, you can use that to generate speech, as we just listened, but you could also use the same kind of architecture to produce music, to generate music. Right? And so on like this. And so if you are using an Android phone and each time there is a voice which is synthesized, you can be certain that there is this wavenet neural network, which is producing the sound that you're actually listening to. There was really a lot of work which was invested into making this architecture work and work on mobile phones, for example. So you can be certain that everything that you listen to, for example, if you use the Google Assistant and it replies in spoken English or in spoken French, then it's actually the wavenet network which is talking to you. Right, and then last slide for today, or last example for today, is this one, which combines not only speech synthesis, but it's a whole system which is basically able to have a conversation with someone else. And so what you will see here is a demonstration of Google Assistant, which was, so this is from 2 years ago, but I still think it's quite impressive. What basically will happen is that the presenter will ask his phone just to take an haircut appointment. That's the only thing he asks. And then the whole system, in this case the combination of several neural networks, will actually call the salon and take the appointment on behalf of that person, right? So let's listen to that.
As I said earlier, our vision for us, we think AI can help with this problem. So let's go back to this example. Let's say you want to ask Google to make you a haircut appointment on Tuesday between 10 and noon. What happens is the Google Assistant makes the call seamlessly in the background for you. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
So how can I help you?
Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd.
Sure, give me 1 second.
Mm-hmm.
Sure, what time are you looking for around?
At 12 p.m.
We do not have a 12 p.m. available. The closest we have to that is a 1:15.
Do you have anything between 10 a.m. and 12 p.m.?
Depending on what service she would like. What service is she looking for?
Just a woman's haircut for now.
Okay, we have a 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
And again, I think the person on the right from the salon, she did not notice or even thought that she was talking to a machine, in this case a bunch of neural networks, because I think this conversation seems so natural, including some language, I don't know how to say that, like this that you heard. You would not expect that from a machine, but that's something that at least here is quite well replicated. Of course, this raises maybe some other concerns, ethical concerns, but I think this is basically where the technology is today, or rather where it was 2 years ago. So now I think you can be quite convinced that this kind of technology is quite mature, or it's getting more and more mature, and it's almost ready for being deployed quite widely from the labs, the research labs, to our phones, to our daily lives. All right, so to summarize what we've seen today, again, I would like to insist this lecture today is a bit orthogonal to what we've seen so far. We should rather see it as some kind of examples of applications that you can implement with the kind of On the other hand, natural language understanding is still one of the most important subfields of AI. So this is why I included these lectures, because this is a very active field of research, and there are still many open problems that we fail to solve properly. Machine translation, speech recognition, and then text-to-speech synthesis can be all framed as instances of a same problem, a sequence-to-sequence problem. All of them can be tackled either with traditional statistical inference procedures, and we've seen a few today, but also I think you've realized that to do that properly, it also requires some kind of sophisticated engineering, which is motivated by some domain knowledge. And fortunately or unfortunately, I don't know, all state-of-the-art methods today are based on neural networks in which this sophisticated engineering usually has been just thrown away. And these methods really reach performance that we could not achieve just a few years ago. Yeah, thanks for the question. So the question is, do you think Google Translate can be better now? How? Well, I think this example that I showed at the beginning, this is something which this one. Well, this is still an issue, right? Let's just do it live if you want. So I'll start from English to French. And so if I type the soccer ball, the window, it broke into 1,000 pieces. Right? This is today's state-of-the-art Google Translate. It's still making errors, right? Because that translation is not correct. A human translator would not say il s'est brisé en mille morceaux. He would say elle s'est brisée en mille morceaux, because this it is referring to the window and not the soccer ball. But to be able to understand this, you really need to understand what's going on in these two sentences, and you need to have a lot of background knowledge to make a proper translation. And that seems something like maybe a little detail, but it's quite profound in the implications and everything that you would need otherwise to properly solve that problem. And so this is just one example, but it's very easy actually to trick this kind of system and making quite funny or just plain wrong translations. Of course, for daily translations of, I don't know, emails or things that are not too important, it works reasonably well to the point that you can use it in practice, and with just maybe a few changes, it's good enough. But I would not say that we are to the point where we can automate everything with a translation system. I would not, for example, Google Translate a whole book. I don't think it would be a good translations. I would not use Google Translate when it comes, I don't know, to poems. I think you would just get garbage out of the system. So there is another question, isn't there a grammatical rule in English saying that the pronoun always refer to the last name in the text? If so, then could we solve this easily? Maybe, I don't know. Maybe there is this rule, but I think even if this rule existed, any English-speaking person would have understood that it was referring to the window and to the soccer ball. And I could reformulate the sentence in the other way, maybe in the other way around, such that this rule is satisfied. I could still trick the system anyway. All right. So let me go back to the end. Right. Also, if you want to know more about neural networks, I invite you to follow my deep learning lectures in the master program, in which we'll just talk about neural networks for 10 lectures, and in which we'll go into way more details than the very few glimpses of the very few architecture that we've seen today. And, if you want to know how they work and why they work, you can follow this class. All right, so that's it for today. Thanks for listening. We will have a last lecture next week in which we'll conclude the course, which will be about artificial general intelligence. So if you don't have any more questions, have a good day and see you next week.